The next thing we're going to talk about is center of mass, but to start that, we're actually going to look at a basic conservation of momentum problem. So in this case, we have a 45 kilogram child running at a speed of 7 meters per second, and they're going to jump onto an initially stationary shopping cart that has a mass of 8 kilograms, and then the two objects are going to be moving together at some final speed. So we can go ahead and set up our conservation of momentum equation. Initially, we only have the one object moving. Afterwards, we have the two of them together moving as a system, so we're going to combine their masses. And we can go ahead and plug in the numbers here, and we end up finding that the final velocity of that system is going to be 5.94 meters per second. So the question now that we have is, in the previous problem, what is the velocity of the system after the child jumps on the cart? Well, that seems pretty obvious. We knew that after the child jumped on the cart, both objects were moving at a speed of 5.94 meters per second to the right, so that's going to be the velocity of our system. However, what is the velocity of the system before the child jumps on? That's a slightly more complicated question because we had our child moving at a speed of 7 meters per second, and our cart was at rest. So what is the velocity of our system? And I realize I'm being intentionally vague here, but could we say the velocity of our system 7 meters per second? Well, that doesn't really make sense because our cart's at rest. Could we say it's 0 meters per second? That also doesn't really make sense because our child is in motion. Maybe we just split the difference here and say it's 3.5 meters per second and say that's the speed of our system, halfway between their two speeds. However, we notice that the cart has a lot more mass, or the child has a lot more mass than the cart. So that doesn't seem fair either. So maybe what we do is we do a weighted average, okay? We take the velocity of the child times the mass of the child plus the velocity of the cart times the mass of the cart and divide by the total mass. And that way, it will proportionally show us the velocities. It's going to average them, but it's going to be a weighted average. And when we do that, we end up finding the velocity of our system is 5.94 meters per second, which just so happens to be the same as the velocity of our system before the collision. That is not a coincidence there, ladies and gentlemen. What we've come across is the idea of center of mass. So I realized in the last slide I was being a little bit vague, and I made a jump here to this idea of center of mass, thinking about the velocity of a system. But that's what we were really getting at, is the center velocity of the center of mass of the system. So what exactly is center of mass? Center of mass is defined as the weighted average of the location of the mass in a system. Okay, so if we have multiple objects in a system, the center of mass is the average position of the mass in the system, and we use a weighted average, kind of like what we did with velocity there. Objects with more mass have a bigger impact on the location of the mass in a system. So we're actually going to talk about this idea a few times throughout the year, but there's really two main uses for it. And the first is when we have a system of multiple objects, okay, so more than a single object. Or when we have objects with a non-uniform distribution of mass. So we might talk about it for like a golf club or a baseball bat, where we have more of the mass at one part of it than the rest. So one of the reasons why center of mass matters, or why it's useful, is that the center of mass of any system obeys Newton's laws. So all those things we talked about thus far related to the motion of objects, free fall, Newton's laws, all of those ideas, okay, are valid for a system of objects if we're worried about the center of mass. Okay, one basic example would be the center of mass of a system will accelerate only if unbalanced forces on the system, okay, cause it to accelerate. So just like an individual object will accelerate if there's unbalanced forces on it, the center of mass of a system will accelerate if there's unbalanced forces on it. So a lot of the ideas we've talked about so far that we've applied to a single object, okay, are going to also be true about the center of mass of a system of multiple objects. So let's look at a few examples here. So one example we have is if we have a non-uniform object such as a baseball bat where more of the mass is towards the end of the bat than towards the handle where you hold it. If we throw that through the air, as baseball players sometimes do, it's going to flip, it's going to rotate, but the center of mass follows that parabolic path that we talked about for projectile motion. So all those equations that we did, all that analysis we did with projectile motion, that's going to be the path of the center of mass of this non-uniform object. Another example would be if we think about the center of mass of the Earth and the Moon as they orbit the Sun. So the Earth and the Moon form a system, and that system orbits the Sun. And we talked about with Kepler's third law that all objects in orbit follow an elliptical path. But the thing that really takes the elliptical path when we're talking about the Earth and the Moon is the center of mass of the Earth-Moon system. Okay? If we looked at the path of the Earth itself, and this is slightly exaggerated, but it takes this wobbly path around the Sun. Okay? It's not quite as pronounced as this makes it seem, but it does take a little bit of a wobbly path. The thing that follows a nice smooth ellipse is the center of mass of the Earth-Moon system. One final application of this, and the one that's the most relevant to what we're talking about now, is that in a case where two or more objects collide or explode and no outside forces act on them, then the velocity of the center of mass of the system is constant because the acceleration of the system is constant since we don't have an outside force. So if we take a look here at this scenario where two objects are colliding, they're moving towards each other initially, and the velocity of their center of mass is 4 meters per second, and again, that's just the weighted average, and we'll talk in a second about how exactly we calculate that. But the velocity of their center of mass is 4 meters per second. After they collide and stick together, they're both moving at 4 meters per second, so obviously the velocity of their center of mass now is 4 meters per second. So it doesn't change because there were no outside forces on the system. We see another example here where both objects are initially at rest. They explode apart, okay, going in opposite directions. But if we did the weighted average, once again, of the velocity of their center of mass, that still is going to be 0. Even though both are moving, okay, it's going to end up canceling out. And they're both moving at different speeds, but again, when we do that weighted average, the velocity of their center of mass remains 0 because there were no forces acting on the system in order to accelerate the center of mass. Mathematically, this is what we're looking at for calculating the position of the center of mass as well as the velocity of the center of mass, okay? And all it is what we've been talking about, a weighted average. So for position, we take the position of the first object times its mass plus the position of the second times its mass, and so on, and we can add up as many different objects as we want, and then we just divide by the total mass. Okay. Same thing with velocity of the center of mass, except now we're using the velocity of each object. We could do it with the acceleration of the center of mass. We could do it with a jerk of the center of mass. It doesn't matter what quantity we're looking at. The way we're going to find it is by doing a weighted average, where we take each individual quantity times its mass, add those up, and divide by the total mass. Alright, so we have a problem here where we're trying to find the center of mass of this system. So we have 3 objects all in a line here. And in this case, an origin or a scale has already been set for us. If we didn't have that, we could set an x equals 0 point and just base it off of that. But here we have a clear x equals 0 point, so we'll just go based off of that. So we're going to go ahead and plug in the things we know. So for each object, we're going to plug in its position and its mass. So there we have all of our numbers plugged in, the position for 1, for 2, and for 3, along with its mass, divided by our total mass. And so we end up getting an x center of mass here of 7.22 meters. So that means the average position of the mass is going to be right about here, and that looks right given the position of the objects and how much mass each one is. So let's bring this back to the idea of conservation of momentum. Center of mass just gives us a new way of analyzing and explaining collisions, okay? So we can look at conservation of momentum to analyze collisions, or we can look at center of mass. Or really, if we wanted to throw in another one, we could also just look at Newton's third law. All 3 are valid. All 3 give us a way of analyzing them. Sometimes one will be easier to use than the other, as is often the case, okay? But both give us a valid way of analyzing a collision. We can either say that the total momentum of the system remains the same if there's no outside forces, or we could say the velocity of the center of mass is constant if there are no outside forces. Both are correct. It's just going to be a matter of which one is easiest to use in a given situation. So let's take a look at a problem where using center of mass is going to be advantageous over using conservation of momentum. So we have a woman here standing in a canoe 1 meter from the back, and what's going to happen is the woman's going to walk from the back of the canoe to the front of the canoe so that she's 1 meter from the front. And we want to know how far the canoe moves during this time. Okay, and we are given this hint, what is the center of mass of the system? This one would be difficult to do with momentum because we don't know anything about the velocity of the woman. Now, we could make one up, but even that would be difficult, and we'd have to then think about how long it would take the woman to cover that distance and then figure out the velocity of the canoe and figure out how far the canoe goes. Doing it with center of mass is going to be easier. So the first thing I'm going to do is I'm going to calculate the center of mass of our system here, the canoe and the woman, and I'm going to say that this left side is my x equals 0 point. So then I have one object here at 1 meter from that point, and then I also have the canoe. Now you might be thinking, where is the canoe located? The canoe obviously spans from here all the way to here, but when we have a uniform object like a canoe, its center of mass is in its center. So the center of mass of the canoe is going to be right here, which is going to be 2.5 meters from that point. So I'm going to go ahead and use my center of mass to find this. So I'll say the woman is object 1, so her mass times her position plus the canoe, which has a position of 2.5 times its mass, all over the total mass of our system, which is 90. And I find that the position of my x center of mass is 1.5 meters. So I have here my position, my initial x center of mass, which is 1.5 meters from the left end. And what's going to happen is when the woman walks to the other side, it's symmetrical. So the center of mass is just going to shift to be 1.5 meters from the right end of the canoe. Now, thinking about what I know about center of mass and the forces acting on this system, I know that there are no forces acting on the system. So the position of the center of mass has to remain the same, which means the canoe must move backwards so that this center of mass here is actually positioned right here, directly in the same spot as the initial center of mass. So how far does the canoe need to move? Well, it needs to move this distance here, which is a distance of 2 meters, since the total length of the canoe is 5. So I'm just doing 5 minus 1.5 minus another 1.5, and that gives me a distance of 2 meters. So that's how far the canoe has to shift to keep the center of mass in the same location. So we have another problem here that we could solve with conservation of momentum, but it's actually going to be most easily solved with the idea of center of mass. We have this railroad car that's coasting frictionlessly down a track, a level track at 5 meters per second, and a box inside the car is going back and forth. Initially it's traveling at 10 meters per second, it hits the front wall of the car, rebounds at 9.5 meters per second, hits the back wall, rebounds at 9 meters per second, and keeps going back and forth until it eventually comes to a stop relative to the car, okay, until they're eventually traveling the same speed, losing half a meter per second each time. And we want to know the final speed of the boxcar system. One quick note, you might be thinking that is there friction between the box and the car? And actually it doesn't matter in this case, because the big idea is that this system, okay, between the box and the car has no outside forces. So even if there is friction between the box and the car, that would be a force within the system, and therefore we don't care about it. So what I'm going to do here is I'm going to calculate the velocity of the center of mass of the system, because I know there are no outside forces on the boxcar system, and therefore that velocity of the center of mass must remain constant. So I know that the car has 9 times as much mass as the box itself. Okay, and so I'm just going to say the mass of the box is m, and I'm going to call that object 1, and it's moving at a speed of 10 meters per second, plus the mass of the car, which has a mass of 9m, and it's moving at 5 meters per second. And I'm going to divide all of that by 10m. So I see here that the m's are going to cancel out, and what I end up getting is that the velocity of the center of mass of our system here is 5.5 meters per second. So what is the final speed of the boxcar system? It's just going to be 5.5 meters per second, because I know that velocity of the center of mass of the system can't change. So when the box finally comes to rest, or within the car, or traveling at the same speed of the car, I should say, they both are going to be traveling at 5.5 meters per second. So the second question asks how many times the box slides off the side of the car before eventually reaching the same speed as the car. And for that, I'm going to think about this. The box starts out at a speed of 10 meters per second and eventually drops to a speed of 5.5 meters per second, at which time the box and the car have the exact same speed. So I know that my change in velocity for the box is negative 4.5 meters per second. And I know that each time it bounced off the side, it lost 0.5 meters per second of velocity. So I'm just going to divide those two numbers, and I find that it's going to bounce off the sides 9 times, all right, with each bounce counting as 1. One last problem here where I have two objects connected by a spring on a frictionless incline. The spring releases, sending the boxes in opposite directions, and what I want to know is what is the acceleration of the center of mass of this system as that spring is sending the boxes in opposite directions. And this might sound like a complicated problem. We have spring forces, we have an incline, there's a lot going on here. However, this problem can be simplified if we just consider this to be a system of M1 plus M2. And then we're thinking only about the forces acting on our system. And the forces on our system are just the normal force and the force of gravity. And this ends up simplifying to a fairly basic spring force problem where we have our components of the force of gravity, Fg sine theta and Fg cosine theta, and all we need to do in order to get the acceleration is set up the sum of the forces in the x direction. So in the x direction, all we have is Fg sine of theta, which is equal to m1 plus m2, the total mass of our system, times our x acceleration. We can sub in for Fg, it's just going to be m1 plus m2 times g, since it's the force of gravity acting on our system. And then we can go ahead and solve for our acceleration. Okay, m1 and m2 cancel out, and we find that the acceleration of our system, which is the acceleration of the center of mass, is just g sine theta. Now, is the acceleration of either object g sine theta? No. Okay, the one going up the ramp has that spring force, so it's going to be less than g sine theta. The one going down the ramp has the spring force pushing it down, so it's going to be more than g sine theta. But the acceleration of the center of mass of our system is just g sine theta.